welcome you all to session 4 of the chapter Ray Optics. Till now we have studied that if a ray of light travels from one medium to another medium, it bends, and that phenomenon is called as refraction of lights. If a ray of light travels from denser medium to rarer medium, its speed increases, and that is why it moves away from the normal. If a ray of light travels from rarer to denser medium, its speed decreases, that is why it bends towards the normal. Right? Knowing all these points, let us go ahead with total internal reflection. Before that, let us study about one concept called critical angle. Critical angle. Okay, and we denote critical angle as seen here. Okay, now let us consider this is the interface of the two media, right? Boundary of the two media. Let me take this medium as denser medium and this medium as rarer medium. We know a medium in which light travels faster, that medium is called as rarer medium, and a medium in which light travels a little bit slower comparative to the other medium, then it is called as denser medium, right? Okay, let me consider source here. And let me consider the rays now here, right? Let me consider first ray which is perpendicular to the surface, and whenever a ray is perpendicular to the surface, it will not bend, it moves in a straight line, right? So we have studied this. If a ray of light incidents perpendicular to the surface, it will not bend, it moves in a straight line itself. Let me consider another ray like this. Okay, this is incident ray. At this point, let me consider normal. If I consider this is normal and this is angle of incidence. Okay, now let us consider a ray is moving from denser medium to rarer medium. What happens? If a ray moves from denser medium to rarer medium, it bends away from the normal. Okay, means it bends away from the normal. Let me take like this. What happens if I increase the angle of incidence like this? So this is a normal and this is angle of incidence. Right? Okay. First thing what you need to understand is, here is, if you increase the angle of incidence, angle of refraction also increases. Right? Okay. At a particular angle of incidence, the refracted ray grazes on the surface. Right? This angle of incidence is called as critical angle. Right? When refracted ray grazes on the surface, then what is the angle of refraction? Angle of refraction is 90 degrees. Right? So this angle of incidence is called as a critical angle. So what is critical angle? We need to know that critical angle is angle of incidence. Do you understand? Critical angle is angle of incidence. So when is that angle of incidence? When a ray of light travels from denser medium to rarer medium. Okay, let me write. When a ray of light travels from denser to rarer medium, see, when a ray of light travels from denser to rarer medium, the angle of incidence at which angle of refraction is 90 degree. The angle of incidence at which angle of refraction is 90 degree, and that angle of incidence is called, the angle of incidence at which angle of refraction is 90 degree is called critical angle. Do you understand this? Is called as a critical angle. So what is critical angle? Do you understand? Critical angle is an angle of incidence at which angle of refraction is 90 degree. It is an angle of incidence at which refracted ray grazes on the surface. Right? So this is called as critical angle. Right? It happens when a ray of light travels from denser to rarer medium. Right? This kind of angle we don't get when a ray of light travels from rarer to denser medium. Right? So if I take a ray of light travels from rarer to denser medium, it moves towards the normal. We cannot get this kind of surface. Right? For example, if I think a ray of light is traveling from rarer to denser medium, what happens? Let me check it out. Rarer to denser medium. Right? So if I am taking, this is the angle. This, let me take, this is the angle of incidence. What happens to the angle of refraction? It is traveling from rarer to denser. means it moves towards the normal. As it moves towards the normal, you will be getting like this, and you will not be getting this kind of angle, right? 90-degree angle of refraction we get when a ray of light travels from denser to rarer, not in the case of rarer to denser, because here the refracted ray moves towards the normal now here, right? So diffracts towards the normal, deflects towards the normal. That is why we in that case we don't get this kind of angle. So critical angle is the angle we get when a ray of light travels from denser to rarer medium, so that the refracted ray moves away from the normal and the angle of refraction becomes 90-degree, right? So critical angle is an angle of incidence at which angle of refraction is 90-degree. Now, let me find what is the equation for this critical angle. How to calculate this critical angle now, right? Okay, let me use Snell's law. What is Snell's law? Snell's law says that the ratio of, right, sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of medium, right, and for a given wavelength of light, and that constant is called as refractive index. Okay, let me use that and let me calculate now. Okay, for example, the light ray is moving from this medium to this medium, so let me take this refractive index as n1, right? Always when I will be considering like this now here. If a ray of light moving from one medium to another medium, the medium in which the light moves, that medium, let me take it as n1, and the medium in which from which the light comes, let me take it as n2, right? Let me consider like this. Whenever I will be drawing the ray diagram, I will be using this, right? Since the ray is moving to this medium, let me take the refractive index of this medium is n1, and from here the ray of light is moving, let me consider this as n2. Okay, shall I use Snell's law? What does the Snell's law say? It gives the formula for refractive index, that is sin I divided by sin R. Okay, let me consider refractive index. What is that now here? N, right? N12 is equal to, what is the formula? Sin I divided by sin R, right? Snell's law. Right, according to Snell's law, we have calculated n12, right? N, it is moving to 1, it is coming from 2. Let me take n12 is equal to sin I divided by sin I. Okay, come on, tell me now here, that is equal to sin. What is angle of incidence? Let me consider that as a critical angle. Yes, okay, divided by. What is sin R? What is angle of refraction? Angle of refraction is 90-degree. Right, if angle of refraction is 90-degree, then what do we get now here? That is equal to sin C divided by sin 90 is 1. So what do you get now here? That is sin C. Right, you know what is the formula for refractive index? We have studied the relative refractive index in the last session. Right, if the formula is n12, the formula is n1 divided by n2. Right, shall I write like this? Right, okay, then what is the formula for critical angle? That is let me take now here, the critical angle, the formula for critical angle is sin C equal to, not C equal to, we are getting sin of critical angle, sin C is equal to n1 divided by n2. What is n1? n1 is the refractive index of rarer medium, n2 is the refractive index of the denser medium. Right, once again, what is the formula for critical angle? Sin C equal to refractive index of rarer medium divided by refractive index of the denser medium. Right, okay, now usually let me consider one case here, right? Okay, let me consider one case. We will be in most of the cases we are considering the rarer medium as air, right? Okay, let us consider if rarer medium is air or vacuum here, right? If rarer medium is air, let me consider what is n1 is equal to 1, right? If what is the refractive index of air or vacuum? That is 1 now here, right? So let us consider if rarer medium is air, usually the rarer medium will be air now here, right? Most of the cases, that is if the rarer medium is air, so what is the value of n1 now here? That is equal to 1. And denser medium of refractive index, what is the refractive index now here? N. Okay, let me use this. In place of, okay, what is sin C equal to, right? Sin C equal to, in place of n1, let me put 1 because it is a rarer medium is air now here, divided by, what is the refractive index of the denser medium? What is the refractive index of denser medium? That is 1. That is, what is sin C? Sin C, what is the formula for sin C? Sin C is equal to 1 divided by n if rarer medium is air or vacuum, right? If both are, it is not air or vacuum, let me use this formula, refractive index of rarer medium divided by refractive index of denser medium. If Radar medium is air or vacuum, and other medium, let me consider refractive index as n. Then what is the formula for a critical angle? Sin C equal to 1 divided by n. Do remember this, right? Sin C equal to 1 divided by n, right? So this is the formula for critical angle if radar medium is air or vacuum, that is sin C is equal to 1 divided by n, right? So this is the formula for critical angle. Okay. Now after understanding what is critical angle, let us move further. Okay. Let us consider like this. If I am considering total internal reflection, okay, the next side reading what we will be studying is about total internal reflection. See here, we are speaking about total internal reflection. It is also known as TIR, total internal reflection. Okay. After studying about critical angle, let me go with total internal reflection. Okay. First thing what you need to understand here is, first ray, if it is 90 degree, it moves in a straight line itself. If you increase the angle of incidence, angle of refraction also increases. At a particular angle of incidence, angle of reflection is 90 degree. What happens if you further increase the angle of incidence? Let me check it out, right? If you further increase the angle of incidence, what happens? If you further increase the angle of incidence, again it moves away from the normal, right? So now it is reflects back, right? For example, if I am taking the normal here, it reflects, right? Instead of refraction, reflection will take place. That is the name, reflection will take place, and that reflection we call as total internal reflection, because it is totally reflected, and internal because it reflects in the same medium. Let me call it, that is why the name total internal reflection, that is TIR, right? Now when reflection takes place, it obeys laws of reflection, that is angle of incidence equal to angle of refraction, right? So here this is the case when angle of incidence is greater than critical angle. Do you understand? If angle of incidence is greater than critical angle, reflection takes place. That is total internal reflection, and this phenomena is called as total internal reflection. Okay, once again, so what is total internal reflection? When a ray of light travels from denser medium to rarer medium, right? Okay, and if angle of incidence is greater than critical angle, instead of refraction, reflection takes place, and this phenomena is called as total internal reflection. Let us consider the definition of total internal reflection. When a ray of light traveling from which medium to which medium? Denser medium to rarer medium. Denser medium to rarer medium. Okay, see here. When a ray of light traveling from which medium to denser medium? Denser medium to rarer medium. Why? Because critical angle, we get that angle when a ray of light travels from denser medium to rarer medium, right? Okay. When a ray of light traveling from denser medium to rarer medium, incidence at the interface of the two media. Okay, let me check like this. When a ray of light traveling from denser medium to rarer medium, incident at the interface of the two media. So what is the interface? This is the boundary of the two medium, right? Okay, interface of the two media at an angle greater than critical angle. Once again, here, a ray of light traveling from denser medium to rarer medium, incident at an interface of the two media at an angle greater than critical angle, then the ray is totally reflected back in the denser medium. Okay, see here. If the angle of incidence is greater than critical angle, then the ray is totally reflected back in the denser medium. This phenomena is called total internal reflection, right? See here, when a ray of light traveling from denser medium to rarer medium, incident at an angle greater than critical angle, incident at the interface of the two media at an angle greater than critical angle, then the ray is totally reflected back in the same medium, that is denser medium itself. This phenomena is called as total internal reflection, and this is the definition for TIR, total internal reflection, right? Okay, so we have two conditions for total internal reflection. Now let us see what are the conditions for total internal reflection. What are the conditions for total internal reflection? Okay, the first condition is that the ray of light must travel from denser medium to rarer medium. Okay, the first condition is the ray of light must travel from denser to rarer medium. Denser to rarer medium. Okay, for this total internal reflection to take place, a ray of light must travel from denser medium to rarer medium. That is the first condition. The ray of light must travel from denser to rarer medium. The second case is angle of incidence. Angle of incidence must be greater than critical angle. The angle of incidence must be greater than critical angle for a given pair of medium. For a given pair of medium. Okay, see, let me consider. Angle of incidence must be greater than the critical angle. Okay, that time itself total internal reflection takes place. Okay, there are two conditions for TIR, total internal reflection. One, a ray of light travels from denser medium to rarer medium. Second one, angle of incidence must be greater than critical angle. Right? Okay, so these are the conditions for total internal reflection. Okay, one thing what you need to understand here, if a ray of light falls perpendicular to the surface, the path is not changed, it moves in a straight line. If the ray of light, right, is incident on a surface in a such a way that angle of incidence is lesser than critical angle, if angle of incidence is lesser than critical angle, refraction takes place. If it is equal to critical angle, it grazes on the surface, right? Angle of refraction is 90 degree. If angle of incidence is greater than critical angle, refraction does not take place, reflection takes place, and that phenomena is called as total internal reflection, right? Okay, we have many applications now here. Okay, let us consider what are the applications of total internal reflection in day-to-day life. Okay, let us consider three applications. The first one is about mirage. The second one is total reflecting prisms. Okay, we will be studying about this in detail here. The third one is optical fiber. Optical fiber. Okay, these are the three applications what we need to discuss now here. The first one is mirage, the second one total reflecting prisms, and third one is optical fiber, and we will be discussing all these three in detail. Okay, now let us check it out. What is mirage? That is, I shall move on to the first one, that is about the mirage. Okay. What is mirage? Mirage is an optical illusion observed in hot summer days due to total internal reflection is called mirage. Okay, first of all, what is mirage? Mirage is an optical illusion, right? Optical illusion observed in hot summer days due to total internal reflection is called mirage. Okay, mirage is an optical illusion, right? Okay, whenever you are traveling in a hot summer day, right? If you are traveling in a car in a hot summer day, you will find that after certain distance, at a far distance, you can feel that there is some water on the road. But when you reach at that point, you can find that there is no water, and this kind of illusion is called as optical illusion, right? So usually this optical illusion is observed in deserts where there is hot summer, right? Whenever you are traveling in the desert, you can find that, okay, after certain distance, at a far away distance, there is a water, but if you go at that point, there is no water, and it was just an illusion. Okay, this kind of illusion is due to total internal reflection. Let me take the surface of a land like this, and let me take a tree here. Okay, let me consider a tree, and I will be observing this tree from a far away distance. Okay, let us take this is a tree, and from far away distance, so I will be observing this tree, right? During hot summer days, the atmosphere will be divided into different layers. Okay, why it is divided into different layers? Let us check it out. During hot summer days, the land gets heated up, right? If the land gets heated up, the layer of atmosphere near the land gets heated up. If this layer is hot, then the molecules move apart, then it will become rarer medium, right? So if I am taking different layers like this is first layer, and this is second layer, and this is third layer, this layer will be rarer compared to this, and this will be rarer compared to this. Why? Because of the heat which is released from the land down here, right? Okay, now let us consider, for understanding sake, let me consider only two layers now here. Okay, let us consider there is one layer, and this is hot layer. Let me take it as a warm layer. Let me take it, this is which medium now here? It is a rarer medium, and this is which medium now here? This is denser medium. Why this layer becomes rarer? Because it becomes hot now here. Whenever this layer becomes hot, the molecules move apart. When the molecules move apart, they become a rarer medium compared to that of the layer which is above that. Okay, this will become denser medium, and this will become a rarer medium. Then, if you are observing the tree, a ray of light which moves from denser medium to rarer medium, the angle of incidence will be such that it will be greater than the critical angle. If the angle of incidence here is greater than critical angle, then it suffers reflection, that too total internal reflection. Okay, it suffers total internal reflection, and you are seeing from here, right? So if you are considering this, let me consider like this now here. If you are so observing from here, and you will be observing the tree like this now, right? So you feel that you can see this from this position, right? Means you can see a tree in this position, right? So if I am considering, if I am seeing like this, you can see this tree, right? Okay, at this position you can see the tree here, right? So why you can see this? Because the ray of light which comes from the tree suffers total internal reflection, right? It moves in this way here, right? This appears to come from this point, and you can see the reflection of the tree, and it feels that okay, there is something water there at that point now here, right? Okay, this happens due to what we say now here, total internal reflection, and this illusion, right, is called as mirage, right? So mirage is an optical illusion observed in hot summer days due to total internal reflection, right? So this is the first application. Now let us move on to the second one, that is total reflecting prisms. Okay, the second one, that is total reflecting prisms. Okay, what are these total reflecting prisms? Let us understand. Total reflecting prisms are a right-angled prism, right-angled isosceles prisms. Okay, see here, these total reflecting prisms are right-angle isosceles prisms which are used to turn the incident beam of light. Okay, what are these? Let us understand. That is total reflecting prism. First of all, they are right-angled isosceles prism. Okay, now right angles, one angle must be 90 degree. Isosceles means two sides will be equal now here. Okay, let us take such kind of prisms, and we shall see what are the applications of these kind of prisms now here, right? Okay, let us take first a prism like this now. Okay, let me consider this is a right angled prism. Okay, let me consider this is a right angled prism, right? Here the two sides will be equal as it is isosceles. Right angle, yes, one angle is right angle, and this is hypotenuse, right? As it is hypotenuse, the other two sides will be equal now, right? as these two sides will be equal, these two angles are 45 degrees and this is 90 degree, right? So this kind of prism is called as right angled isosceles prism, and in that we are studying about total reflecting prisms. Okay, what happens here? Let us check it out. Okay, so these two sides will be equal. Now let me consider there is an object here. This is an object. Let me consider AB is an object, right? Okay, let me consider a ray which comes from here, right? Okay, this ray is incidenting perpendicular to the surface, right? If a ray of light incident perpendicular to the surface, it do not deflect here, right? So there will not be bending of light, right? So that is why this ray moves forward, right? Let me take like this. So it reaches at this position, right? When this ray incidents on this hypotenuse, the angle of incidence will be greater than the critical angle. If angle of incidence is greater than critical angle, then it suffers total internal reflection, right? So it suffers total internal reflection and it reaches at this point. When the ray reaches at this point, again this angle is 90 degree. As it is 90 degree, it moves in a straight path, right? Okay, let me take a ray from here, right? Let me consider beam of light, because the rays will be coming from the object here, right? So incident beam of light, let me consider like this. Again the ray here, since it is perpendicular, it moves in a straight line like this. Then again it suffers total internal reflection as the angle of incidence is greater than the critical angle. Okay, then you can observe this in this position. This is A, right? Okay, let me consider as this is A, the image will be like this, right? So let me consider it as A dash and this is B dash. Means this right angle prism is used to turn the incident beam of light through which angle here? 90 degrees, right? If the object is here, you can see the object from this side here, right? So let me consider like this. Right angled isosceles prisms which are used to turn the incident beam of light by how much degrees now here? By 90 degrees, right? By 90 degree you can turn the incident beam of light, right? This is the ray diagram, right? To turn the incident beam of light through how much now here? 90 degrees, right? Usually in periscopes you can find the application of right angled prisms now here, right? Okay, let me go with the further things now here, right? Okay, now let us check it out. What happens if you take a different kind of right angle prisms now? Okay, let me consider this now here, right? This is a prism. Okay, let me consider here so that it will be clear to you all. Let me consider this is a right angled prism. Let me consider this is a right angled prism. So the two sides must be equal here, and this is 90 degree. Let me consider this is 90 degree and these two sides will be equal. Now let us consider the ray diagram here, right? If I am considering the ray diagram, if this is an object, let me consider this is an object. Again, let me take the same ray diagram. Let me take the object nearby. A ray of light which incidents on the surface is perpendicular, so it moves in a straight line itself, right? Again, when it reaches at this position, the ray is moving from denser medium to rarer medium. When a ray of light is moving from prism is a glass, here there is air. A ray of light is moving from denser medium to rarer medium and angle of incidence is greater than the critical angle. That is why it suffers total internal reflection. Let me take like this. It suffers total internal reflection. Again, this angle is not 90 degree here. So again the ray of light is moving from denser medium to rarer medium. Again the angle of incidence is greater than critical angle. Then again the ray of light suffers total internal reflection. At this position the angle of incidence is 90 degree. That is why the ray of light will not bend and it moves forward like this, right? Okay, let me take the ray of light from here. Let me consider this is A and this is B now here, right? Okay, let me consider like this. Let me take again a ray of light here. This is ray. Since it is 90 degree, it moves forward. It suffers total internal reflection the same way as I told earlier, and again it suffers total internal reflection. It reaches at this point, and again as angle of incidence is 90 degree, it moves forward. Now the image is observed like this. So this is B now here. Let me take this is B dash and this is A dash as I took here. Here we are turning the incident beam of light. Let me consider like this. We are turning the incident beam of light through 180 degrees. Here we have turned the incident beam of light through 90 degrees, right? 90 degrees we have turned. Here the incident beam of light is turned by 180 degrees. Right? Okay. These are used to turn the incident beam of light by 90 degrees and also by what we say here 180 degrees. Right? So here there is an object, but the image of the object can be seen here. Right? So we are turning the incident beam of light by 180 degrees, and for this we will be using the total reflecting prisms or right angled isosceles prisms. So this is a ray diagram to turn the incident beam of light by 180 degrees. So this is for 90 degrees and this is for 180 degrees. Now let me take another one ray diagram. Okay, this time let me keep prism like this, right? So this is the hypotenuse, and let me consider this is the side here, and this angle is 90 degree, and let me take consider this is 90 degree, right? So right angle isosceles prism here, right? Okay, now let me consider the object is here, right? Okay, let me draw the ray diagram. If I am considering here and the ray which is incidenting on the prism, let me take the first ray like this here, it is incidenting on the prism. Now the ray of light is moving from rarer medium to denser medium, because this is air and this is glass now, right? If it is moves from rarer medium to denser medium, if I am taking normal here, right, the ray of light is moving from rarer medium to denser medium, means the refracted ray bends towards normal, right? So this is normal, and it bends towards normal like this. Okay, let me remove this so that there will be no confusion, right? So now the ray of light suffers refraction, right? It moves from rarer medium to denser medium. Now when the ray reaches at this position, right, now the ray of light is moving from denser medium to a rarer medium. When a ray of light is moving from denser medium to rarer medium and angle of incidence is greater than the critical angle, it suffers total internal reflection. Okay, let me consider it suffers total internal reflection and it reaches at this position here, right? Now let me take here, the ray of light is moving from denser medium to rarer medium, right? So as the ray of light is moving from denser medium to rarer medium, the refracted ray must move away from the normal. Okay, let me take where actually the normal is now here. This is the normal here, right? If this is normal, the ray of light must move away from the normal, right? As it moves away from the normal, so it reaches at this position. Okay, let me remove this, and it moves away and we will be reaching like this. Okay, the same ray diagram let me take from the bottom of this object now. Let me take this is A, B as the object now, right? Okay, let me consider here, this will be the ray, it reaches here, it suffers a refraction, and as angle of incidence is greater than the critical angle, it suffers again what we say here, total internal reflection, and the ray is moving from denser medium to rarer medium. The ray must move away from the normal here. As it's move away from the normal, so you will be getting the image like this. This is A, so like this. This is A dash. Let me take it as B dash. If you want to invert the image of the object, if the object is like this now, right? If the object is like this, the image will be reverse of that, right? If you want to invert the image of the object, we can use right angle prism. Okay, let me state like this. What are total reflecting prisms? These are right angled isosceles prisms which are used to turn the incident beam of light by 90 degree. We have seen the ray diagram, 180 degree, or to invert the image of the object, or to invert the image of the what we say here object, right? If you want to turn the image of the object, and this is the ray diagram, right? We have seen the three ray diagrams in case of total reflecting prisms. Do you understand what actually happens here, right? So these again these are the applications of TIR, total reflecting prisms, and the principle which is used in total reflecting prisms is total internal reflection. Okay, this is all about second one. Let me move on to the third application, that is optical fibers. Let me consider like this, optical fibers. Okay, what is an optical fiber? Let us check it out. Optical fiber is a device. Okay, let me consider. Optical fiber is a device used to transmit light in any desired path. Let me consider like this. Optical fiber is a device used to transmit light in any desired path. So if you want to transmit the light in any desired path, we can use optical fibers, right? So this device is called as optical fiber, and the principle what we are using here, right? Okay, let me take it. The principle which I am using here is total internal reflection, right? What is the principle used in optical fibers? That is total internal reflection. How it works? Let us check it out, right? You have seen the optical fiber. Optical fiber is a thin pipe, let me call, right? It is like the thickness of your hair, right? It will be a thin fibers, right? For example, in many of the decorative items, we will be using the optical fibers, right? So you have seen the optical fiber is nothing but it will be like a pipe, right? Okay. The size, the thickness, do you understand? The thickness will be of the thickness of the hair here, right? That much more the thickness will be. For understanding sake, let me take thickness like this. This is an optical fiber, right? Okay, let me consider like this. It is used to transmit light in any desired path, right? Let me call, if I am considering the pipe is a device used to transmit the water in any desired path. In the similar manner, it is a pipe which is used to transmit light in any desired path. Okay, how does it transmit? Let me check it out. Okay, and this manufacturing this optical fiber, we need to understand there will be a layer here, right? Let me consider it is made up of two kinds of layer. This is one layer and outside there will be another layer, right? So this is called as core and this outer is called as cladding. Okay, let me consider this is a core and that is the cladding here, right? Okay, so this there will be two layers here, that is the first layer, and there will be outer layer here, right? Okay, and it is manufactured in such a way that this is having high refractive index, right? This core is having high refractive index, means it is a denser medium, and this cladding will be of a low refractive index, right? Means it is a rarer medium. This is denser medium and this cladding is the rarer medium. Right? Okay. Now what happens if a ray of light moves inside this pipe here, right? Okay, let me consider like this. Right? This is a high refractive index. Let me consider this is a pipe here, right? This is of high refractive index. Let me imagine there is a surface here, right? Okay. Now, if a ray of light incidents here at this position here, right? If a ray of light is incidenting like this, if a ray of light incidents like this, where is a normal here? Here there is normal. A ray of light is moving from which medium to which medium? Rarer medium to denser medium. If a ray of light moves from rarer to denser medium, it bends towards the normal, right? It bends towards the normal, right? It bends like this, towards the normal line, right? Okay, now the ray of light is moving from denser medium to rarer medium. This is denser and this is a rarer line, right? And when it moves from denser medium to rarer medium and angle of incidence is greater than the critical angle, it suffers a total internal reflection. In that way itself, the optical fibers are manufactured, right? Such a way that if a light is incident at any point, it must suffer TIR, total internal reflection, right? It suffers total internal reflection and it falls here. Here also the ray of light is moving from denser medium to rarer medium, and again the angle of incidence is greater than the critical angle, it suffers total internal reflection. Again here also it suffers total internal reflection, and lastly it comes outside here, right? So it comes outside. Again it is moving from denser medium to rarer medium and it moves away from the normal, right? For example, it moves away from the normal, right? From here we got the light at this position here, right? Means inside the optical fiber total internal reflection takes place, right? This is how it works, right? So by this device we can transmit light in any desired path, right? So there are many applications of optical fibers, right? For example, for endoscopy, for example, if I'm taking in a medical field, right? So the endoscopes, whatever we use in a medical field is the application of what we say here, optical fiber, right? So what is present inside our body we cannot see, but if you send the optical fiber through our mouth and if you check it out, if you send the light, we can get the image of whatever is present inside the body, right? That is called as endoscope here, right? So for that purpose we are using this optical fibers, and another application is we are using optical fiber to get the internet connection nowadays, right? So because the light moves with the speed of 3 to 10 raised to 8 meter per second, right? We get the data in a quick time, right? That is why we are using optical fibers, right? So the broadband connection what we get at our home, so that is through optical fibers itself. They will be getting a wire in which they will be having many optical fibers. Through that we will be getting the internet scenario, right? So nowadays we are depending upon optical fibers a lot, right? So optical fiber is a device through which we can transmit light in any desired path, and the principle which are using in optical fiber is total internal reflection. So these are some of the applications of total internal reflection. Thank you.